Okay, so when we're talking about electricity and the variables that go into creating a circuit, we're going to be looking at four things in particular. The first is current, electrical current. You can compare current like with a river current, how the current of a river tells us how much water is flowing and how quickly it's moving. We're also going to look at voltage. That one would be the equivalent of water pressure. We'll talk about that one. We're also going to have resistance, as well as something that you guys are probably familiar with, but wattage, or watts. Now, I'm just going to throw out as a disclaimer that as we learn about circuits and electricity, we're going to be looking at the simplest explanations possible, just enough that we can get stuff done with it. So I'm going to kind of oversimplify things. Now, what we're looking at here is an example of what conduit, like a wire, would look like. Or a conductor, rather, of electricity. So one of the things that's unique about metal and what makes it a good conductor of electricity is that it allows for electrons to flow more freely through its material. So what we've got here is kind of like the parallel bars would be a wire, that'd be our metal conductor, and then inside we have 3 atoms. There would be obviously way more atoms, however, for visual purposes, I think this will do just fine. So when you have an atom, if you remember back to science, you have in the middle this green area is the nucleus. That's going to consist of your protons and your neutrons, and the electrons kind of circle in orbit almost around the nucleus. Now, in metal, those electrons have the ability to move. And it's kind of like when you have 2 magnets of the same polarity, if you try to push them together, they're going to naturally repel each other. So as electrons move from a power source, whoops, we're going to turn this off, and I'm going to grab this little red guy here. So as the electrons move from their source down the conductor, as they get closer to the existing electrons, it's going to push that electron further away, and then this one will flow down, and it'll force this one to move this direction, and then this one will move and so on and so forth. What this does is it creates forward movement or motion, and that is what we would call electrical current. So when we're talking about electrical current, we're looking at the flow of electrons from a power source to a ground along a circuit. So we see that these electrons are going from one end, for example, of a battery to the other end because they're pushing each other one at a time. Now when we refer to electrical current using math, there's an equation we're going to use, and I apologize in advance. You guys know math is not my forte, so we're going to make this as easy to understand as possible. But with electrical current, we're always going to reference it in equations with the letter I. Now, electrical current itself is measured in something called an ampere, or otherwise known as an amp, right? So you guys might have seen this before too, amps. The symbol for amps is just the letter A. Now, when we're talking about an ampere, it's a unit of measurement. So we're measuring how many electrons are moving at any given second. So the equation is actually that 1 ampere, or ampere, is equal to, and you don't have to write this one down, but it's 6.25 times 10 to the 18th power. Now, if you were to do 18 decimal positions with zeros, that equals something to the effect of 6.25 trillion electrons that flow every second. So for every amp, we have 6 trillion electrons. The more amps you have, the more electrons are moving, the more electricity that it is providing. Now, we know that circuits are created by having a continuous loop, a connection with conductors. We use this as an example of a simple series circuit, that the electricity flows from the negative end of the battery, that's where the electrons come from, they flow through our conductor, they go up and through our light bulb, and then they end up making their way back down to the positive end of the battery. The next thing that we have to look at, though, is what actually moves these electrons? What actually forces them to go? What's the force that pushes them? Now, if you imagine that there's a wall in this battery that separates the negatively charged electrons, and then on the other end you have the positively charged protons, the electrons are going to be drawn to those protons. The amount of draw creates force, and what that force really is voltage. Now, when we're talking about voltage, we're looking at the pressure from a power source that pushes those negatively charged electrons, or that electrical current, through a circuit. So when you look at the electrical current, you're kind of looking at what exactly is it. So we're looking at how many electrons, how fast they're flowing. When you're looking at the voltage, you're looking at kind of like the how. How is it that those things are moving? The voltage will determine how much energy is moved along those lines. Now, the thing about voltage is that it's really telling us how much energy is being transferred per amp. So for all those electrons that are moving, how much is actually being converted into energy? We measure that in units called volts. And the symbol for volts is just the letter V. Voltage is a lot like water pressure, so it's the thing that kind of pushes those electrons through to their end source. Now, if we go back to this example of our pretty straightforward or pretty simple circuit here, our conductor rather, the thing about metal that makes it a good conductor is that it does allow those electrons to flow so freely. But in reality, they don't flow as neatly as I showed you on the first slide where I had this same image. In the first one, I showed you that the electron comes in and it bumps the next one down the line and so on and so forth. That's what happens in a nutshell, but that's not the way that it actually ends up happening because you have all these electrons flowing and it's not a guarantee that they're going to end up jumping neatly from one atom to another, if I can grab the right thing. Really what ends up happening here is that these electrons flow very freely throughout the course of the conductor and as a result might bump into certain obstacles that are in their way, or they might run along the edge here and end up coming in contact with the insulator, which is then going to slow them down. In both cases, these electrons lose some of their potential energy, so they kind of bounce around more freeform, and as they do, we see something called resistance. Now, when we're talking resistance, we're talking about the reduction of electrical current as it passes along a circuit. Imagine having, for example, hurdles on a track. When a runner runs up to those hurdles, the amount of time that it takes them to go over that hurdle slows down their overall time, which is resistance. It resists their overall time. Now, if we were to translate that to electricity, we look at the loss of potential energy. So the signal kind of becomes weaker over time. Now, resistance is measured in units that we call ohms, O-H-M-S, named after the guy who came up with the law of resistance. And the symbol for that is the Greek letter omega. So that's going to represent ohms. Now, the more ohms there are, the more resistance there is, which means less energy is delivered to the end location. There's a formula that we're going to use for resistance, and you can go ahead and fill this into your resistance formula section down at the bottom of your sheet. But really what we're looking at is the letter R, so we're looking at resistance, and my pen's kind of lagging here. R is equal to voltage divided by the electrical current. I'll show you what that looks like in just a sample, or in just a second rather. Some other formulas that we need to grab down real quick. So we've got our formula for resistance, and we know that that equals voltage over the electrical current. It's kind of like algebra where you can move x from either side of the equation to the other side, and it works the same way. So I'm going to have you write down that electrical current, the formula for current, is equal to voltage over resistance. We basically swap resistance and the electrical current. Now, if we were to get and isolate the voltage on its own, we would end up with voltage is equal to the current times the resistance. Right? So that's telling us how much energy is flowing versus how much is actually making it through. That's what our voltage is actually measuring. How much energy is being transferred per amp. Now that's a lot of hypothetical information, but I want to show you why it's important that we know this and how we're going to be using it. Now I've got the same type of a simple series circuit that we've used before, but instead of a normal light bulb, I now have an LED, a light emitting diode. You might already know that LEDs are very energy efficient because they consume very little amounts of electricity, which is why a lot of homeowners are starting to use them today because it saves on their energy costs. The thing though is that if you pumped the same amount of electricity to an LED as you do for a normal light bulb and there's no way to resist that electricity, it's going to end up burning that light bulb out. It's going to literally fry the connection inside that light. It could either burn it, it could set it on fire, or in worst case scenario, it could even cause a mini explosion. So to avoid that, we use something called a resistor. Now this resistor right here will kind of eat up some of the electricity as it makes its way from the source to the fixture and then back to the source again. Now I'm going to use this formula to try to figure out what size resistor we need. How much resistance do we have to put on this circuit? Now batteries, you're going to learn, all batteries have a voltage, all of these standard batteries rather, have a voltage of 1.5. So we know that the volts are equal to 1.5. You can look up online how much electricity that this LED is capable of handling, and this particular one can handle 0.03 amps. Right, so we've got 1.5 volt battery. We have a light bulb capable of consuming 0.03 amps. Now, if I use that resistance equation, resistance is equal to the voltage divided by the electrical current by the amps. I can do the math on this, and if you run the math on your phone real quick, you're going to find that the resistance is equal to 50, and we use ohms as the expression. So we need a resistor that is at least 50 ohms in order to slow down the electricity enough so it won't fry our LED. Now, when we talk about LEDs and how much energy they're capable of handling, we're also referencing their wattage. And what wattage is a measurement of electrical consumption, and we express it in units called watts. Now, the symbol for wattage is just a W, so you'll see on light bulbs if you go to the hardware store that they're all rated with X number of W's on there, so the letter W. And wattage is equal to the electrical current times the voltage. Now, I want to give you a real-life example, one that I've had to learn in renovating my houses. So I've had to redo some of my electrical circuits. Now, in your house, you probably have an electric breaker panel in your basement or in a utility closet somewhere, and in that panel are lots of different switches. Now, all houses are supplied by DTE with 110 volts of electricity. Let's see if my pen will work for me here. 110 volts of electricity. When it comes into your circuit breaker, you can choose how much of that is sent to individual circuits. The most common switch type is a 15 amp switch. You could also get a 20 amp switch, or a 30 or a 40 or a 50. If you have a large oven or stove, you have a 50 amp switch. If you have just normal outlets, you only have probably a 15 amp switch on there. Now, if you do the math on this means that I have up to 1650, up to 1,650 watts that I can put on that one circuit. If I were to go out and buy 16 100-watt light bulbs, I could light all of those light bulbs without losing any power, like the brightness of those bulbs. And I could light them on this one circuit. But if I add 17, there's a chance that the circuit's going to shut off. And you might have experienced this before, where if you have too many things plugged into one electrical circuit, that's going to shut off those circuits, because the circuit breaker can sense the overload and heat, and instead of catching fire, because there's too much energy trying to be drawn through that device, it triggers the switch, and then it ends up shutting the whole circuit down. We'll take a look at wattage as the fixtures that we put onto our electrical circuits.